Hey everyone, it's Dr. Carroll here. Welcome to Chemistry 1111. This is Unit 7, Lecture 3. We're looking at bonding here involving three centers, so three nuclei, and p orbitals talking to each other such that pi orbitals are forming in a delocalized system. So this is on page 335. And we don't do all the details about this, but we'll look at a bit. So the pi molecules, let me get my pen here, so far involve two atoms, so the orbital pictures look like the same. For the localized bonding model applied to ethene and the MO approach applied to molecular oxygen. But we can have some pi orbitals spread over more than two atoms, three or more, and that would be a delocalized pi orbital system. So they form when more than two p orbitals overlap in an appropriate geometry. So we're going to look at a few examples of that. We'll start with ozone, and here we have two resonance structures of ozone, and there's 18 valence electrons. Bond angle is a little less than 120. You can have the localized sigma bonds shown in 736b, right? So that's a sigma bond. Then there's an oxygen, sp2 hybridized, it's the central atom, and we form the sigma bonds between the sp2 on the central atom, oxygen, and a p orbital on a ligand oxygen. But we still have p orbitals left over. So two of these sp2 orbitals forms, okay, we said that. The third sp2 hybrid contains a lone pair of electrons. We said that. I can even make the lone pair in there. The Lewis structure also indicates the presence of a pi bond and 5 non-bonding electron pairs on the two outer oxygens. Okay, so how do we deal with that? The sp2 hybridized inner oxygen has one unused 2p orbital, which is perpendicular to the plane, and this p orbital is in the perfect position to form a pi bond through side-by-side overlap with a p orbital on either outer oxygen atom. So you get two resonance structures. Each outer oxygen is equally good for the overlap. But it's misleading to think that there are two different ones. All three overlap simultaneously, the nature of the wave function. So neither the Lewis structure nor the localized bonding gives an adequate description. MO theory does, and it allows you to talk about the overlapping. You have three overlaps, so you predict you're going to have bonding and anti-bonding molecular orbitals. But what about the third one? Well, the third one we call non-bonding. Okay, so let's look at a picture here. And on the top of page 336, we have the bonding MOs where the p orbitals are all overlapping nicely at the top and bottom. A anti-bonding one where you don't see nice overlap happening, and then something called the non-bonding where they really aren't talking to each other at all. And so in the other resonance structure, the third lone pair is on the right outer atom, while the double bond on the left, to the left outer atom. The double bond appears in different positions in the two structures. And one of the lone pairs also appears in different positions. So if you look at that closely, you can see that. And we're going to just, again, we don't get into all the discussion here, except to say there is a third orbital called a non-bonding orbital, where the lone pair is in a different position of the resonance structures. And summarize, let's just summarize. The interactions among the three p orbitals of ozone generate three molecular orbitals, of which the pi and pi non-bonding are filled, and the pi star anti-bonding is empty. And the bond length in ozone provide evidence that the pi electrons extend over the entire molecule rather than being isolated between the two atoms. Bond lengths are around 128 picometers, so it's in between a double bond in O2 and a single bond typically in H2O2. So therefore you're extending between a single and a double bond. This business about a composite model I don't really see the point to discuss that. I don't think that helps us at all. So I'm going to leave that part out and jump to the next part. I mean, it's just a different idea to get things started, but really doesn't help us much in terms of what we're already talking about. So let me get to the other part here. Again, that section 7.5 was supposed to be a brief introduction. We didn't get into all the nitty-gritty, but I wanted you to at least see the idea of delocalization in ozone. You can get extended pi systems where you have alternation of single and double bond, and that is called conjugation. So a delocalized pi system is present whenever p orbitals on more than 2 adjacent atoms are in position for side-by-side overlap. Okay, so in their position, if you have alternating single and double bonds. Butadiene is an example of that, used in the synthetic rubber industry. The Lewis structure of butadiene contains 2 double bonds and sequential pairs of carbon atoms. So that's one way to get a conjugated system and to get delocalization. So if I look at it, I have, here's butadiene. I have carbon, one carbon, another carbon, so you have a double bond, single bond, a double bond. I don't care about the ligands so much as the carbon backbone. So double, single, double, single. And here we see we don't see the pi part of it. This is the sigma framework of the carbons. They're all sp2 hybridized. So there's my sigma framework, 1, 2, 3, 4 carbons. And then I have my pi bonding. So you have these overlap above and below the plane of the 4 carbons. And I think there's going to be a thunderstorm any minute now. I'll see if I can finish this before we get a power failure. Or snowstorm, or whatever kind of storm you want it to be, because I have no idea what time of year it is right now. So we have these MOs forming this conjugated system. Okay, so Louis just mentioned that you form these pi MOs, and the antibonding MOs are empty. Whenever the Lewis structure of molecules shows double or triple bonds alternating with single bonds, the bonding description includes delocalized pi orbitals. Molecules that have alternating single and double bonds, like butadiene, are said to have conjugated pi systems. Okay, each double bond in a conjugated system adds 2 electrons to the corresponding set of delocalized MOs. So here's an example of one methyl methacrylate, and we see here that we have, is it conjugated? We got single, we got double single, single single. No, it's not conjugated. This is going to be localized. Analyze the pi system. Okay, just draw it and talk about the hybridization, and you'll see that they say there's conjugation. Where is their conjugation? I don't see the conjugation. Form a set of 4 delocalized. So I'm looking back here. I mean, I guess part of the molecule is conjugated, but it's not extending across all of the system here, right? I have a double, single, double. That's not a full one here. About double, single, double. No, that's not good either. You should be able to verify. Let's look at this a bit more closely. The 2-stage 3 sp3 hybridized. Yeah, I got 1, I got 2. Then I got an sp2, an sp2, and an sp2. Inner oxygen is sp3. Outer oxygen, well, you can just write that as a 2p atomic orbital. Okay, so that was just all the assignments of all of those. So Summing all those contributions, the 14 sigma bonds and 2 sp lone pairs account for 32 of the 40. So there still are some p unhybridized orbitals. One single bond separates the two double bonds, which signals conjugation and delocalized pi orbitals. One single bond separates the two double bonds. Yeah, okay. Here's the single bond. It's separating these two double bonds. I agree with you. But that's not over the whole length of the molecule. Maybe I'm overthinking it. Maybe it doesn't have to be over the whole length of the molecule. So this is just partial delocalization. And that's all that has to say. Okay. Practice exercise. Won't bother with that now. Each molecule, so bonding in the molecules is more stable by having a delocalized pi system, but it doesn't have to run through the whole molecule. But if it does, double, single, double, then that portion is more stable because of the delocalized pi system. It's like you're getting greater reinforcement by making that happen. Stronger bonds. Carbonate. You have Lewis structure, so you got single, double. Well, page 342. I don't really see why 4-atom delocalization network can have a central atom surrounded by 3 other atoms with which it interacts. So this resonance structure here, central atom with 3 other atoms with which it interacts, and that is an example of a delocalized system. So that's a different setup. We have 1,4-pentadiene, 1,3-pentadiene, the one which is then pentane. Okay, so that's just a bit more about CO3 2-, showing various resonance structures. And then the other one is showing the framework for the 1,3-pentadiene. Okay, so that is more stable than 1,4-pentadiene because of the conjugation. Larger delocalized systems, again, you're looking for a big repetition of single, double bonds here. Plastoquinone on the right here is an interesting molecule. But it is not, there's 2 singles in a row. You got vitamin A, that looks like there's more conjugation, right? Because you got a single, double, single, double, single, double, single, double, single, double. So that's good. Retinol, double, single, double, single, double, single, double, single, double, single. That's good. So those are conjugated. Conjugated portions of the molecule, right? It doesn't have to be the whole molecule, but the portions of the molecule are highlighted in purple here. Beta-carotene, which is the precursor, so it's needed to make vitamin A. So again, you see double, single, 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 double, single. So that is an example of an extended one. Benzene is a delocalized system. C6H6, benzene. And so you have, here's 2 resonance structures. These are also called Kekulé structures, after the guy who imagined benzene as being this ring. I think he had a dream where there was a snake, and the snake was eating its own tail. And it said, oh, I now know how the benzene structure works. So you have this framework of sp2 hybridized carbons all the way around, making a hexagon. And then you have these unhybridized p orbitals on each benzene. And so you see the reds all smeared together, and they give you this portion above the plane, and the blue, so that's the other phase of the wave function, all smeared together, so you get the bottom. and that's benzene. And the quick way to write benzene, and some of you may remember this from grade 11 organic chem, is just with this hexagon with a circle in it. So this is a classic delocalization system as well, and it has increased stability. Often delocalized systems have colors to them, which is interesting. Okay, and then we get into the band theory of solids. So those topics, you won't find that many questions on them, but it is good to know. And I'm going to do something I haven't done before. I'm going to go to a movie answering a question from the end of the chapter. Now the question number has been changed, so this was a different version, but it'll still give me what I want to have here. So I'm going to go to I don't know what the way that is showing here. Cancel that. So I'm going to just play this. And now I realize that I didn't have computer sounds on it. So I'm going to have to make this a little addendum, and then I will put them together. Or maybe the computer sounds I did live on. Okay. Okay, you know what I'm going to do so I don't have to piece together two things? I'm going to go back to the beginning here, and I'm just going to narrate it. How about that? I'm not going to listen to this guy. I'm just going to narrate what's going on here. So these are molecules that may have been in one of the focus sections. So the question is, are these atoms going to be delocalized or not? Will they have significant sections which go single, double, and these are larger molecules. And here we have this one about termites, and we see that there isn't a double, single, then you have a whole bunch of singles going through. So no, that one's not good. Oh, the guy actually has his own little arrow, and he's talking it through. So this molecule here is not having significant delocalization. Okay, so that's called Neosembrine Termites. It's like wastes of termites. They're marking their territory. Here's a sex attractant for both moths and elephants. Okay, we have a double bond, and everything else is single bonds until way at the end. That's another double bond, but those p orbitals are way too far away from each other to have any delocalization. So this molecule is not going to exhibit delocalization. This next molecule here is pinene, and it is a smell in pine forests, and there's a double bond, and it's sort of a weird looking molecule, but you don't see conjugation there. Limonene, you got double, single. No, you got too many singles between. So limonene is not a delocalized pi system. Geraniol, let's see, we're close. No, double, no, it's too far away. So there's too many singles. Double, single, 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 then double. So that one is not good. Polyisoprene, that looks like it might be good. We got double, single, oh, but we got two singles and then a double. So that one isn't going to work. So forget about that one. And do we have another one after that one? Xanthan. Oh, xanthan, that's good. Okay, that one is delocalized pi electrons. So we got double, single, double, single, double, single, all the way through. So xanthan is one where you do have a large exhibition of conjugation. It's a delocalized pi system, which makes it more stable than if it wasn't delocalized. So there's my narration, and I'm sure it's just as exciting as what the other guy gave. And that's the end of that one. So that's the end of this lecture. Hope you had fun.